For Unit 12, Day 1 notes, we're going to talk about polyhedron. Polyhedron is a space figure or a three-dimensional figure whose surfaces are faces. So we have like this 3D shape, and we see that what makes up the sides of it are called faces. The vertices are the little corners, and the edges here are like line segments. So if I were to look at this example 1, and I wanted to know how many vertices, edges, and faces there are in the polyhedron, I need to count them, and I need to list them. So for faces, we have the bottom one, which is 1, and then we have 4 triangles, so that's 4 and 1 make 5. Okay, for vertices, we have 1, 2, 3, 4, 5. For the edges, we have 1, 2, 3, 4, 5, 6, 7, 8. And then here it says, for key concept, Euler's formula. The sum of the number of faces and vertices of a polyhedron is 2 more than the number of its edges. So basically you're saying F plus V equals E plus 2. So how many vertices, edges, and faces of the polyhedron at the right have? Okay, well, let's count them. So for faces, we have the top and the bottom, so that's 2. And we have how many rectangles? So 1, 2, 3, 4, 5, 6. So 6, 7, 8. So 6 rectangles and then 2 hexagons. Vertices, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then edges, I'm going to start here with this one. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so now let's plug it into the formula. If I had F plus V equals E plus 2, if I plug these numbers in, will it work? So F is 8, V is 12, E is 18. Does 8 plus 12 equal 18 plus 2? Yeah. So we counted correctly because it worked out in our formula. So in example 3, if I just use the formula to figure out the faces, I just want to plug in the numbers that I have. So F plus V equals E plus 2. I know E is 8. I don't know F, and V is 5. So 8 plus 2 is 10. If I subtract 5, the number of faces is 5. In part B, a polyhedron has 4 faces and 6 edges. How many vertices does it have? Okay, so here we know it has 4 faces. We don't know how many vertices, and it has 6 edges. So if I subtract 4 from both sides, the vertices are 4 vertices. Okay. For this part, similar solids. Similar solids have exactly the same shape, but not the same size. 2 solids are similar if the ratio of the corresponding linear measurements are equal. So in example 4, it says determine whether the solids below are similar. If yes, give the scale factor in simplest form of the first figure to the second figure. So we're going to compare all of our sides by fractions. So if I'm going to go from the first figure to the second figure, so this one to this one. So it looks like we have 3/6, 3/6 again, 2/4. Okay, so all of these fractions reduce to 1/2. So since they're the same fraction, yes, and then we have to give the scale factor, so the scale factor is 1/2. Okay, in part B, let's compare first figure to second figure. So 2/3, 3/6, 2/3. Alright, well that reduces to 1/2, and those can't reduce, so since they are not the same fraction, no. They have to all equal the same thing. Okay? In part C, we're going to compare like parts. So if I have a diameter, I compare it to this diameter. So they gave me the radius. So my whole diameter is 20. So I have 24/20, and then 30/25. Now for 24 and 20, 4 goes into those, so that would be 6/5. 5 can go into these two numbers, so that would be 6/5. So since they are the same fraction, yes, they are similar solids, and the scale factor is 6/5. Okay, part D, going to compare linear measurements here. So we have the height of the pyramids here in the middle. So 12/3. Then we have this side, which is a smaller side, so 8/2. And then we have the longer side of the base of 20/5. So let's see, 4 goes into 12/3, so that'd be 4/1. 4 goes into 8/2, so that'd be 2 goes into 8/2, so that would be 4/1. 4 goes into there, but so let's do 5. So 5 goes in 4/1. So since they're all 4/1, yes, they are similar solids, and their ratios are 4/1.